the title of the project is Development of Photoacoustic Spectroscopy System and Underskin Imaging Application. So we wanted to create a biodetection system. Biodetection systems are mainly used in health industry nowadays, but they come with their problems. One of them is some of them are harmful because of the radiation they use, and most of them are really expensive, like the MR machines in hospitals. So we wanted to create a biodetection system that is harmless, low cost, and portable. For this, we decided to use photoacoustic effects, and we use piezoelectric material to measure the photoacoustic effects for the reasons that I'm going to explain. So photoacoustic effect is basically the notion of sound emission from an object on which light is reflected with intervals. What happens is basically when light hits the intended target, in the material a heat increase occurs. With this heat increase, an expansion also occurs in microscale. And because of the intervals when there is no light hitting the substance, cooling occurs and so contraction occurs. With this continuous expansion and contraction, a pressure wave forms which can be detected as an acoustic wave, and so sound is emitted. A piezoelectric material is a substance that generates electrical charge from the mechanical stress applied on the piezoelectric material. So we decided to use the piezoelectric material because the sound emitted from the substance is basically a mechanical effect on the piezoelectric sensor, and so we could measure the sound with the piezoelectric material by the electric that the piezoelectric material generates. For the procedure, we have two main sections. The first one is the identification of the properties of the piezoelectric sensor. So we wanted to identify the properties of the piezoelectric sensor, mainly its resonance frequency, because the sound emitted from the substance was so low, and we wanted to achieve full efficiency. For this, we created the system shown here. A laser ray is sent to the piezoelectric sensor, which also gets reflected to a photodetector. When the laser hits the piezoelectric sensor vibrates and moves. With this movement, the laser reflected from the piezoelectric sensor also changes its angle, and we can measure that change by the photodetector. Where the most change occurs is where the piezoelectric sensor vibrates the most, and thus we can find the resonance frequency, which we used for the frequency of the light we sent to the sample. And we measured that frequency as 3 kHz. So for the second section, we first designed the signal generating circuit. We didn't want to use a signal generator because we wanted the system to be portable. So we designed a circuit with the help of a 555 timer integrated circuit. We also designed a signal amplifying circuit, which is shown here. A basic signal amplifying circuit, because the value and the magnitude of the sound coming from the sample was so low, and we wanted the most accurate results. So the last design of the photoacoustic measurement system is shown here, and this is a photo of it. So there is a RGB LED which we use as our light source. There's a piezoelectric material which has a hole going through it. Under the piezoelectric sensor there is a sample, and the sensor is connected to a computer. We send the light through the LED, going through the hole of the piezo sensor and hitting the sample. The sample emits sound, the piezoelectric material records and generates electricity and sends it to the computer. We used an oscilloscope program for signal measurement in the computer, which is called sound card oscilloscope, and this is a screenshot of it. So for the results, first of all, the piezoelectric material measurements. Here the vibration amplitude and the frequency of the light is shown. We see that when frequency is lower, the signal amplitude is actually bigger. But our sound card didn't measure signals lower than 20 Hz, so we had to find the optimum high frequency. And in this chart, we can see that when frequency is in the 3 kHz range, we actually see the biggest signal amplitude. And this is a relative vibration amplitude, not the direct signal amplitude. So for the measurement system data, we first took measurements with samples prepared with food colorings because it is the mainstream application used in these types of measurements. So here we can see that the data of the white sample is actually lower than the other samples, and that's because white reflects most of the light coming through it, so lower absorption occurs in contrast to the other samples, and a lower data is shown. This proves that we could use photoacoustic effects for measurements like this. In the second table, we see the measurements taken with the samples that were covered by chicken skin. We used chicken skin so we could detect if this measurement would work with samples covered with biological tissue. So here we can see that in example in a red sample color, we see that the red light and green light has lower data than blue light. And this bigger potential difference, and with this bigger potential difference, we can see that we can identify red area with blue light, for example. So, in conclusion, a measurement system was designed and built in order to identify the resonance frequency of the piezoelectric sensor, and the low-cost, harmless, portable measurement apparatus, a biomeasurement system, was formed. For future considerations, the system can be improved by using a laser diode, insulated cables can be used, and the system can be combined with a structure like a microscope for detailed imaging and scanning. Thanks.